Okay, so now I can't yell. Okay, thank you very much for having me here. My name is James Forbes. This work was done with my PhD student, David Zlotnick. So the title of my talk today is Signal Point Kalman Filtering on Matrix Lie Groups applied to the SLAM problem. So what motivates a lot of this work is autonomous vehicles. We can have autonomous vehicles for surveillance or reconnaissance or exploration of Mars, drone delivery, underwater inspection of infrastructure like dams or bridge abutments or even ships, material handling in warehouses, as shown here. And to realize autonomy, you really have to solve three problems, which is the guidance, navigation, and control problem, or I prefer to say the navigation, guidance, and control problem. So what is navigation? Navigation is the process of extracting a best state estimate, so something like position, velocity, angular velocity, given noisy and bias or imperfect sensor data. What guidance is given the best estimate of where I am, and I know where I want to be, what is the path I should follow. And control is, given this path I want to follow and the best estimate of where I am, how do I actually follow that path? Okay, and what's important to realize when you're trying to do navigation, guidance, and control is that navigation is an input to both the guidance step and the control step. So basically, if your navigation solution is really poor, then your guidance and your control tends to be quite poor as well. So navigation is really important. So as I said, some people would say that basically the guidance step and the control step is really simple as long as your navigation solution or your estimation solution is very, very good. So that's what motivates making sure you have a really good state estimate, which is why there's thousands and millions of papers on state estimation and why the Kalman filter is such an important engineering tool in the real world. So what makes state estimation hard is, as I mentioned, your sensor data is never perfect, ever, and you're often dealing with nonlinear systems. And also it's important to realize that sensors rarely measure exactly what you want. So for example, there's no such thing as an attitude sensor. There's no such sensor that will give you a measurement that's on the group SO3. Okay, so you have to use other sensor measurements to infer what is, for example, my attitude. What is the element of SO3 that I'm trying to estimate? Okay, so that's what makes state estimation hard. Okay, so I just want to kind of review the standard tools, and I'll start with just the standard Kalman filter. So when we're talking about Kalman filtering, we're talking about a discrete time process model shown here, and a discrete time measurement model shown here, where W and V are distributed according to here with covariances Q and R. So what the Kalman filter does is it gives you a state estimate in a predict and correction structure. So here's the prediction step. So basically I take my process model, I take my best previous estimate and my input, which could be a control input, something like a force or a torque, or it could be an interoceptive sensor, something like a rate gyro. And I get a predicted state estimate, and along with that predicted state estimate, I get this covariance, which is a measurement of, or a measure of my confidence in my state estimate, okay? And what's important to realize here is these are expectations, and these are really integrals, okay? And that plays into what I'm going to talk about later, which is signal point Kalman filtering. Okay, so that's our prediction. And then we do what's called the correction. So we take our predicted state estimate, we take that predicted state estimate, we plug it into our measurement model to get us a predicted measurement, and we compute what's called the innovation here. We take that innovation, multiply by the Kalman gain, add that to our predicted measurement, and get our corrected measurement. Now what's important to realize here is if my state estimate and prediction step was absolutely perfect, then that means the innovation term would be 0. Okay? Because the measurement minus what I predict the measurement should be would be 0. Okay? That's never going to happen because of noise in the system. So really what this is doing is that you're taking your predicted measurement and you're correcting it using some other data. Okay? To compute the Kalman gain in the linear sense just boils down to this, which is really just a cross covariance involving the predicted error and the innovation, as well as the covariance associated with the innovation. And then finally, I can get the covariance associated with my corrected state estimate, which is this given here, okay? Which is just, this statement just comes from this previous statement here. And all these can be derived in many different ways. Like if you pick up this book by Jasinski, Jasinski derives the Kalman filter 5 different ways, okay? Often the Kalman filter is referred to as BLUE, the best linear unbiased estimator, and it's best in the sense that it minimizes the trace or the Frobenius norm of covariance, and it's a linear unbiased estimator. Okay, great. The truth of the matter is there's no such thing as a linear system. So when we're confronted with a nonlinear system, what do? There's many approaches to approximating the Kalman filter, one of which is what's called the extended Kalman filter. So basically what you do is you predict using your nonlinear process model. You linearize, compute these Jacobians. You can then compute this predicted covariance. You can then do a correction step where in the innovation term you use your predicted state as well as your measurement model, and you can compute the Kalman gain and the covariance associated with the corrected state. So that's one way of doing things, is you use a Taylor series expansion associated with the nonlinear measurement model. Another popular way to do this is what are called the sigma point techniques. The UKF, which we already heard about, is a special kind of a sigma point Kalman filter. There's something called the cubature Kalman filter. At the end of the day, all these sigma point methods are approximating the integral in the expectation. So like a Gauss-Hermite, just pick any quadrature method, and you can basically make a sigma point Kalman filter out of it. So like there's like a Gauss-Hermite quadrature Kalman filter. There's lots of different versions. Particle filters are essentially approximating that integral in there with a lot of particles. But at the end of the day, that's all these sigma point algorithms are doing, is they're approximating this integral. So today I'm just going to talk about sigma point algorithms in general, although in my numerical results, I'm going to use actually the uncentered transformation. Okay, so a sigma point transformation, how does it work? At the end of the day, we're going to approximate this and this, so the mean and the associated covariance. So whether you do that, as for example, the uncentered transformations, the first thing you do is you use a Cholesky decomposition to decompose P into some sort of matrix square root. You can then compute these sigma points, where when you're dealing with a state that's an element of Rn, you can just add the mean plus this scaling term times this column matrix here. And then you do the same thing with a subtraction. Now, just kind of fast forwarding a little bit, if this isn't an element of Rn, but rather some sort of group, you can't do this, right? Okay, so you have to adhere to the group structure if you want to do this, which is what we're going to talk about in a little bit. So once you compute these sigma points, you pass the sigma points through this nonlinear measurement or nonlinear function f here, so you get these, I call them xi pluses, or these script pluses. And then to compute the mean, you just sum them up with a weight, okay? And here I think it's pretty clear why you're approximating an integral. Like you're basically taking this integral, which is in this expectation operator, shown here, and you're essentially approximating it by a finite sum times a bunch of weights, okay? And then you can do the same thing for the covariance as well. And again, if x is an element of Rn, then yeah, sure, you can do this sum, no problem, or this subtraction with the sum, no problem. But if x is an element of some sort of matrix Lie group, then you can't do this. Okay, so to summarize the sigma point Kalman filter, of which the cubature Kalman filter, the uncentered Kalman filter are a special case. You compute sigma points, which I'm denoting as x and w here. You pass these sigma points through the nonlinear process model. You recombine the sigma points that have been passed through in a weighted fashion to get your predicted state as well as an associated covariance. Then you do the exact same thing again for the measurement model. So you recompute a set of sigma points. I'm recomputing sigma points x and v here. You pass them through the measurement model. You can compute your predicted measurement. This then goes into an innovation term, but also you have to compute these cross covariances and the covariance associated with the innovation. So here's the covariance associated with the innovation, and here's that cross covariance associated with the state and the innovation. And then we can just do the correction step as we usually would, and the covariance computation associated with the predicted measurement in a pretty straightforward manner. Okay, so now getting to kind of the more interesting part of the talk is how do you do this on just a generic matrix Lie group. Okay, so let's just solidify some notation. So let G denote a matrix Lie group. I like to think of SO3, which motivates a lot of this work. Let little g denote the matrix Lie algebra associated with G. I'm going to use this notation S as follows. So we can take any element of the matrix Lie algebra, and we can write it as S of A, where A are the components associated with capital A, okay? So this S is going to be really helpful in some of the notation later on. With this definition of S, which maps Rn to the matrix Lie algebra, we can define the inverse operation, which maps the matrix Lie algebra to Rn. Associated with the matrix Lie group G is the exponential map and the matrix logarithm. So exponential map maps the matrix Lie algebra to the matrix Lie group, and the matrix logarithm maps the matrix Lie group to the matrix Lie algebra. So we have this relationship here. And also we can define how to extract a realization. So if you have some sort of nominal member of the group G, you can draw samples xi here and use the definition of S. So this is going to be an element of Rn, S as a function of xi is going to be an element of the matrix Lie algebra, and then we can use the exponential map to then draw a sample. Okay, so those are just the tools. So how do we then do sigma point Kalman filtering, or just how do we do the sigma point transformation on a matrix Lie group? So again, what we're trying to do here is we're trying to basically approximate this integral, but ways to make things a little bit more complicated is our nonlinear function f is a function of g, like x is an element of the group G, and f maps G to G. Okay, so we're going to do what we did before, which is we're going to take our covariance P, we're going to do a Cholesky decomposition, generate these columns. We're then going to compute sigma points, and what we have to do here is we can't quote unquote add like we do in Rn. So we have to adhere to the group structure, so we're going to do a multiplication here. So we're going to take our mean, and then we're going to use this definition of S as well as the exponential map to then generate these other sigma points shown here, okay? Then what we do is we pass those sigma points through the nonlinear function f, okay? So now we have these transform sigma points, okay? Now, we can't just take those transform sigma points and add and subtract them because we have to adhere to the group structure of the problem. So to compute the mean, we actually have to solve this problem here, this optimization problem here, or I think of it as an optimization problem here, where D is some sort of a distance on G, which usually is going to be the geodesic distance. But one of the points of this paper was to point out, especially in SO3, there's other ways to solve the problem other than like using an iterative method when your distance is the geodesic distance. So that's how we're going to have to compute the mean somehow. And then to compute the covariance, the first thing we have to do is define the distance or some sort of error between our mean and the sigma points that have been transformed. So the way we do that is through this equation here, where I essentially want to extract out E, okay? So E is an element of Rn, S of E is an element of the matrix Lie algebra, and then exponential map of all that is an element of G. So essentially we just rearrange this equation. So now I'm just rearranging this equation, yada, yada, yada. Okay, I can extract E. Great. Once I've extracted E, I can then compute the covariance. Okay, so once we have that structure available to us, we can now do matrix Lie group sigma point Kalman filtering. So here's our nonlinear process and measurement models where X is an element of the matrix Lie group G. To execute the prediction step, we compute some sigma points, pass them to the nonlinear motion model or process model. To get the predicted mean, we have to solve this optimization problem, which there's iterative methods to do this, okay? But in the special case of SO3, you can actually do some simpler stuff. And then again, we compute this, what I'm calling E minus, to then compute the covariance associated with that mean value. Then to do the correction step, what we do is, again, we generate some sigma points, X minus and V, pass them through the measurement model. This is the measurement is assumed to be an element of Rn or Rny, if you will. So we can still compute that predicted measurement as we previously would have. We can then compute the covariance associated with the innovation. Now, to do the cross covariance, we've got to be a little bit careful. We have to compute this error here, but we have to compute it using the tools of the matrix Lie group. So again, we're going to use what I showed in the previous slide, the method to compute the error, basically using the matrix logarithm and then S inverse to extract this E. So then we compute this cross covariance here. Now we can compute the Kalman gain. This is also pretty important that usually we'd write X hat is equal to X hat minus the prediction plus the Kalman gain times the innovation. The way to think of it now is that's our X hat minus, that's our corrected state estimate. This obeys the rules of the group right here, this multiplication here, and this is an element of the matrix Lie algebra. So you got to think of this as an element of the matrix Lie algebra, which is why we're writing it like this, okay? And then again, we have the covariance update associated with the correction step. So this is how you do essentially sigma point Kalman filtering on matrix Lie groups. And even though I'm writing most of this using what's called the uncentered transformation, this holds for pretty much any sigma point method, okay? Okay, so now I want to apply what we've talked about here to what's called the SLAM problem. SLAM is short, an acronym for simultaneous localization and mapping. So what we want to do is we want to figure out where a vehicle is in a room or a forest or somewhere on Mars. we want to figure out where the landmarks are, so where all these chairs are or where the walls are, and actually estimate not only where the chairs are and the walls are and the pillars are, but also estimate the position and orientation of the vehicle relative to that set of landmarks we are trying to estimate as well. So we're simultaneously localizing, so where's the vehicle, the position and attitude of the vehicle relative to the landmarks, and mapping, where are the landmarks relative to each other. That's the simultaneous localization and mapping problem. In the robotics community, SLAM is really divided up into kind of two parts, a front end and a back end. The front end is really vision algorithms, like feature extraction, things like that. And the back end is essentially the estimation procedure. So what we're talking about here is I'm kind of sweeping under the rug the whole front end problem, which is it's challenging. I'm not saying it's easy, but I'm sweeping that under the rug, and I'm just focusing on a back end, which is this matrix Lie group SPKF being applied to the SLAM problem. Okay, so here's the setup of the SLAM problem. So we have some sort of datum frame and datum point W. Here's our vehicle with a body frame denoted by the basis vectors B1, B2, B3. I have some sort of camera at point T, and this camera can observe landmarks. And also attached to the body, I have an IMU, a rate gyro and accelerometer. So some notation, I let the position of point Z relative to point W resolved in frame A be denoted by this, and then the position of Z relative to W resolved in frame B denoted by this, and then the relationship between those two is given by what I call a direction cosine matrix. Some would call this a rotation matrix. I'm from, I did my PhD in aerospace engineering, so I tend to use aerospace notation. This direction cosine matrix is an element of the matrix Lie group SO3, which is defined here. So what are some of the associated tools we're going to use for SO3? First thing we're going to do is define the matrix Lie algebra, little SO3. I'm going to define this subcross operator. Some might use a hat to denote the cross product here. We can use Rodriguez formula to write the direction cosine matrix in terms of an axis A and an angle phi. This Rodriguez formula, you can actually just show that this is basically equal to, or not basically, this is equal to the exponential map. There's actually a really nice problem I give on my homework assignments of showing this exactly equals this using the Cayley-Hamilton theorem and stuff. It's really nice. Anyway, we can also have the matrix exponential. So we have the matrix exponential here. We can have the matrix logarithm, and so we have this relationship here. I have extra minuses kind of floating around, especially that minus, because of the way I'm defining the direction cosine matrix, which is the attitude of the body frame relative to frame A. A lot of people in robotics would put a plus there, and then that's just the attitude of the frame A relative to the body frame. So it's just the transpose, basically. Okay, so the SLAM problem. So I have to define a couple things. So here is my position update given a velocity measurement. Here's my velocity update, or not necessarily a velocity measurement, but a velocity estimate maybe. This is my velocity update given an accelerometer measurement here, okay? Now an accelerometer doesn't measure inertial acceleration. An accelerometer measures inertial acceleration biased by gravity, which is why I have the gravity vector here. The discrete time relationship between the previous attitude and the next attitude is given by this expression here, where xi is going to be related to a rate gyro measurement plus noise. And then the map positions are described here, where I have my previous estimate of the map location and the correction. So basically now, because I'm running out of time, I'm going to skip some of this. You can plug all of this into this matrix Lie group sigma point Kalman filter. So basically we have the predicted position, sigma points, predicted velocity sigma points, predicted attitude sigma points, and predicted map location sigma points. Now, R, V, and M, they're all an element of R3, so we can just add, how we usually would. But to compute the attitude, we have to solve this problem. Now, you don't have to use D, the distance D as a geodesic distance. For example, if you use the chordal distance, okay, so we're going to use the chordal distance here, you need to solve this problem. Now, what's really nice about this problem is if you kind of go through the math and you read with this objective function like this, it turns out that this has the exact same structure as what's called Waba's problem in the aerospace literature, and there's a known closed form solution which is given by a singular value decomposition, which I'm showing here. So I would argue that that's pretty nice because you don't have to do any iteration. You can just do an SVD and Bob's your uncle. Another thing you can do, actually I'm not going to talk about it because I'm out of time. The point is that there's easier ways to do this, one of which is an SVD, and there's another way that the aerospace guys like that involves the matrix Lie algebra. But I'm out of time, so I'm not going to talk about it. Okay, so now we can do the correction step as we usually would. So here's the correction step. Here's the correction step as we usually would, where again, we're being very careful about adhering to the group structure when we're doing additions and subtractions, which is why we have this here and this guy right here. Okay, so now I just want to show some numerical results. My colleague Tim Barfoot, he has a nice lab with a motion capture system. So basically we're taking this sensor head, which has these reflective balls on it, and a camera can see where those reflective balls are to give us some ground truth. On top of this sensor head, we have a camera and an IMU, and we're going to observe these landmarks on the floor in the lab. So here's some results. Ground truth is given in green, and the dashed blue line is the UKF. Or the sigma point Kalman filter, and we can see that we converge very, very quickly, and we get really, really good tracking. This is the RMS error of the landmarks, so we can see that the RMS error of the landmarks is decreasing quite quickly. So after 2 minutes, we're down to less than 5 centimeters worth of error in the landmark location. And now my student David, who's a MATLAB guru, put together this nice simulation. So you can see that the blue triangles, which is the estimate of the landmarks, they converge pretty quickly to the true landmark locations. And the estimate of pose, it's not quite converging, but after a little while, you're going to see that it converges pretty close to the true pose as well. So yeah, now it's converging pretty quickly. And you can see all these squares and diamonds, they're lining up really close as well, showing this convergence. So that was all I had to say today. If there's any questions or time for questions, I'd be happy to take some questions. Okay, so we're lucky because we have, especially on SO3, we have Rodriguez formula. So we have this nice closed form solution where we can extract out like this axis and an angle, and you essentially, you define it to be, there's a way to, essentially you force that angle to be only between either 0 and 2 pi or between minus pi and pi. Okay, so for the special case of SO3, which is really what I'm interested in, you can essentially force it to be unique. But in general, yeah, I don't have a good answer for you. But for SO3 and SE3, yeah.